Welcome back to my class. Today we will be talking about three different things. Firstly, we will talk about the different types of variables like local variable, global variable, static variable, external variable, and register variables, which are categorized based upon the extent of existence, or rather the scope of the variables. So first we will be discussing about the scope of these variables, and followed by that we will talk about the assignment operator today. The assignment operator is basically the equal to symbol that we often use in our program, but there is a basic difference between the assignment operator and the equality in case of computers programming. When we talk about equality, it is usually given by the double equal to symbol in C programming language. And when we are using single equality symbol, it means that it is an assignment. That means whatever is the content of the right hand side of that equality symbol gets stored in the left hand side variable. In order to understand the working of the assignment operator, we will see a demonstration. But before that, let us go into the scope of variables. So in order to understand the scope of variables, we already have a program written down. So I just called it vaddemo.c. Now here, as you can see, right at the beginning we have got the hash include stdio.h. We have included the stdio.h header file because we will be using the printf function, which is a system defined function, and it is declared in the header file stdio.h. Now we also have a global variable declared over here. Global variables are usually declared outside the main function or outside any other function. So we have GL as a global variable declared here. Next, we have declared another function over here called the add function. The name of the function is add, and it takes two parameters. Both of them are going to be of type integer, and it also returns back an integer. Now inside the main function, we have declared three local variables, local 1, local 2, and sum local, and we have assigned the values 5 to local 1 and -7 to local 2. We have also assigned the global variable GL a value of 10 over here. After this, we are calling the sum local or we are calling the add function from here, and the control is supposed to jump over here. Now here inside the parameters list, here we have mentioned two variables, int a and int b. Both of these two variables are also called local variables because the range of these variables are within the existence of these variables are there only when the function is within the scope of this add function. Inside the add function, we have declared another variable count, which is going to be again of integer type, but we have used the keyword static before it, making it a static variable. Now the beauty of static variables are that no matter how many times this function is being called, the initialization of the static variable happens only once, and it retains the value that was originally given to it. So we are initializing it with the value count, and this is going to get executed exactly once, only when this particular function is going to be called for the first time. Now, after coming into this function, after the initialization of the static variable, we are now incrementing the value of the global variable by 5. That means every time the add function is going to be called, the value of the global variable is going to get incremented by 5. And also we are incrementing the variable count, which is of static int type, and then we are returning the value of summation of a and b. So when we go back to the calling of the function, let's see how many times we are calling it. So this is the first time we are calling the function, and after the function call, we are displaying the value of the global variable and the sum. And this is the second time, third time, fourth and fifth time. So 5 times we are calling the function as a whole. So let us see how exactly it works. So I'm saving this program, and I'm coming out of the VI editor. BCSE102L. I have compiled it. Let me compile it with the .o extension so that I can give a suitable executable name to it, suitable name to the executable file. So var underscore demo, enter. So /var demo, enter. So as you can see right at the beginning, the global variable GL had the value 10. So once we entered the function 10, this value 10 is displayed along with the value of the count variable, which happens to be 0. Next, what happens in the add function, we are incrementing the global variable by 5, so GL becomes 15, and the sum is calculated to be minus 2. So that is what is displayed inside the add function. This is for the this is what we get after the first function call. Now after the second function call, this is what happens. So when we go back to the calling function, go back to the main function, there we have seen that second time when we are inside this add function, here we can see that the count has been incremented to 1. Here we can see that the count has been incremented to 1 and GL has now become 20. Okay, and sum remains as minus 2. Again, for the third time, the count becomes 2, then the count becomes 3, count becomes 4, and every time the global variable's value also goes on increasing. Okay, so finally it stops at count equal to 4, and when GL becomes equal to 35. This shows that there is an existence between the this shows that there is an existence between the this shows that the global variable exists throughout the duration of the program, and so does the static variable. So every time the function gets called, the static variable retains its old value and it processes on the basis of that particular value, or it works on the basis of that particular value. So this is all about local, global and static variables. But there are two more things that we want to discuss over here. First one is the external variable, second one is the register variable. So in order to experience or in order to see the usage of external variables, we will process this particular code once again, but with the -e flag. Now, in our first lab session, I have already showed you that when we try to stop the execution right after, when we want to stop the compilation process right after the pre-processing phase, we use this -e flag. So once I do that, at the bottom you can see that this is the piece of code that we have for the add function, and here we have got the main function, and here we have got the declaration of GL and add function. But before that, the hash include stdio.h has been replaced by the content of the file. So as you can see here, the usage of the extern keyword. So the usage of this extern keyword makes the variable associated with it have existence even outside the program. So these variables are defined or declared inside the header file stdio.h, but when we are compiling this, automatically those variables also have existence in our program. So in order to do such a thing, we use the extern keyword. Now that's about extern. Now we will look into the register variables. So in order to understand how the register variable works, let me remind you that we have already told that a variable created in the register memory is what we refer to as a register variable. Now register memory is a part of the CPU, and it is the costliest form of memory, and also it is the closest to the CPU. So the access time is minimal. And hence, when we write the assembly language code, or when we take a look at the assembly language code, it's there that we get to see these register variables. So in order to perform an operation, what the CPU usually does, it fetches the value of the operands from the main memory to the register memory. So it writes it down into some of the register variables. It performs the operation on the register variables, and then it sends the value back to the main memory. So in order to see those register variables, let us now compile the program once again, and we shall stop right after the assembly language code will be generated. Now in order to do so, we use the -S extension. So GCC -S var-demo.c. This is going to generate the var-demo_.s file, which is written in the assembly language. Now let us open this var-demo.s. If we do that, here as you can see that we have got quite a long file over here, and these values, these x29, x30, w0, w8, w9, x8, w9, x0, x9, extend, these are the variables which are often called the register variables. So with that, we come to the discussion on various types of variables. The next topic that we will be talking about is the assignment operator and its demonstration. So for that, I'll write a program and I'll again get back to you. Okay, so for that we have written here a placeholder.c file. So let's see here, hash include stdio.h, and inside the main function we have written one integer of type int, a float f, a character c of holding the value f, and an unsigned int uy holding the value 3. Next we are displaying the value of I as %d, f as %f, and here we are displaying f as %1.2f and %10.2f. Finally, we are showing the character as %c and the unsigned integer value as %u. Note that here the value of the floating point number f has got 1, 2, 3, 4, 5, 6, 7 places after the decimal. Now let's compile it. So done, and let's just run it. So here what do we see? See, I equals to 50 as expected. When we see the floating point number, here 1, 2, 3, 4, 5, 6. So as you can see, the 7th bit has been chopped off. If we take a look at the 7th bit, you can see that the last 2 bits are 3 and 8. So if we go for a rounding value, that means this one should have been 7, 4, but that is not what is happening. So the 7th bit is simply just chopped off. Now when we look at the 1.2f, %1.2f, that 0.2 actually signifies that there will be only 2 decimal places after the decimal point. Okay, so that's why here you can see we have got a rounded number. So if this was more than 4, it would have come as 1.313. And 1.2 means what? The minimum width of the string or minimum width of the floating point number should be 1. So here, since it is more than 1, that 1 of that 1.2 that has been ignored. But in this case, when we have the 10.2, so you see for the 0.2 we have got 2 places after the decimal, and for the 10, here the total width should be equal to 10. So in order to make the total width equal to 10, what has happened here is padding of spaces. So some spaces have been padded over here to make the total length of 10 characters. Finally, C is displayed as the content of C is F, so F is displayed over here. Note that the quotations are not over here anymore, and UI, that is the unsigned int, is given as 3 over here. Now since we are calling it to be an unsigned int, if I try to make it a signed one, you will see that the value will get something completely different. So if I give just -3 over here, I save it and I recompile it and I try to run it again, you can see that the value of UI is something like this, which is again definitely not 3, right? So unsigned integers don't support signs. So when you give minus sign, it is representing something different, some other value. Okay, so now let's start discussing about the operators. Well, C supports 3 different kinds of operators. They are namely the unary operator, the binary operators, and the ternary operators. Now when we talk about the unary operators, the first operator that comes to our mind is the size of operator, which we have already discussed in our previous lab session. Apart from this, we have got the double equal to, the double plus, the double minus, and the tilde symbol, which are the unary operators present in C. We will see one by one how they work. Coming to the ternary operators, we have got one ternary operator in C, which is mostly used in case of if-else combination of statements. So when we learn about branching statements, we will talk about the ternary operators. After this, we have got the binary operators. Now when we talk about the binary operators, there are quite a few binary operators. The first one being in the list is the assignment operator or the equality. Apart from this, we have got the arithmetic operators: plus, minus, multiplication, division, modulus. We also have the relational operators: less than, greater than, less than equal to, greater than equal to, double equal to, not equal to. These relational operators are usually used in case of branching statements like if-else. Along with these relational operators, we also have some shift operators. Shift operators allows us to perform bitwise shift left or bitwise shift right. We also have logical operators like double ampersand or double pipe and not. Double ampersand usually means logical and, pipe means logical or, and not obviously means not. And we also have the bitwise operators. We have got the single ampersand, which implies the bitwise and, single pipe, which indicates bitwise or. Again, the shift operations, shift operators, left shift and right shift, tilde and caret. These are all bitwise operators. The caret here is bitwise XOR operation. Now coming to the variants of the assignment operation, we have got variants of the assignment operator. They are plus equal to, minus equal to, star equal to, slash equal to, modulus equal to, right shift equal to, left shift equal to, and percent and equal to, XOR equal to, and OR equal to. We will see how they work in one by one, looking into the various kinds of assignment operator. So I have already written a program for this purpose. Let me just open it up. Here I am calling it assignment demo.c. So in this program, let us see what I have done. Firstly, we have declared three local variables n1, n2 and n3, and we have assigned the values 3, 4 and 5 to them. Next, what we have here is n2 minus equal to n1. Now, when I write n2 minus equal to n1, this actually means n2 is equal to n2 minus n1. Okay, so when I do this, what happens is that the right hand side of the assignment operation, that is n2 minus n1, this is first computed, this expression is first computed. So when I do n2 minus n1, it is 4 minus 3, which is equal to 1. So n2 gets to hold the value 1. So when I try to print this statement, value of n2, I expect that the value of n2 will be displayed as 1. Next, what I do, I write n1 plus equal to n3. Now what this means is n1 is equals to n1 plus n3. Now n1 happens to be 3 over here and n3 is 5. So when I write this n1 equals to n1 plus n3, actually n1 plus n3 gets computed, which is equals to 8, and this 8 gets stored in n1. So here this one holds the value 8. After this, what we have is n2 into equals to n1. This again means that n2 will be equals to n2 into n1. Now what is the last value of n2? Well, the last value of n2 that we have encountered here is 1, and last value of n1 is 8. So when we multiply n2 by n1, we get 1 into 8, which is equal to 8, and this 8 gets stored in n2. So therefore, when we display this n2 over here, we are expecting to get the value 8. After this, what we have is n2 right shift by 1. So what does this mean? n2 right shift by 1. What does this mean? Let us consider the least significant byte of n2. That least significant byte is basically the last byte, and it is going to hold the value something like this to represent the value 8. Now if I try to perform a right shift operation by 1, that means what? There will be a 0 coming in from the left side, and the rightmost 0 is going to get removed from the variable. So this means that there is a right shift operation that has taken place, and if we try to compute the value of n2 now, this binary value is equivalent to the decimal value 4. So when we try to print the value of n2 now, we are going to get 4. After this, we are again performing a left shift. This is actually mean here something like this: n2 left shift by 1 byte, by 1 bit. So when we do that, that means again what we have here is something like this: 5 zeros followed by 1 0 0. Now when we perform a left shift, automatically the leftmost 0 gets removed and 1 0 appears in the right hand side. This is what regenerates the value of n2 to be 8. After this, we have got n2 equals to n2 mod n3. Now n2 is 8 and n3 is 5. So when we try to perform the mod operation, 8 divided by 5 gives us a remainder of 3. So that remainder 3 gets stored in n2, and hence the value 3 should be displayed. So when we try to print this, the values should come something like this. It should come as 188483. So let us see if that's what we are getting. So as you can see, 188483. That's exactly the value that we were expecting to come, and that's exactly what we got.